Okay, so for self-test 3, number 3, Gottfried is driving a car of mass 1.2 to the power 3 kilogram at 65 kilometer per hour down a hill inclined at theta equals to 18 degrees from the horizontal. Gottfried sees a stop sign ahead and pulls his foot off the gas pedal and slams on the brake, bringing the car to a complete stop at 3.7 seconds. What is the magnitude of the force exerted by the brakes to bring the car to rest? Okay, now what we have here is the car, and then the mass of the car is 1.2 kilogram. The speed was 65 kilometers an hour down a hill inclined at theta 18 degrees. See the stop signs ahead and pulls his foot off the gas pedal and slams on the brake, bringing the car to a complete stop in 3.7 seconds. So we have here the force, the brake. What is the magnitude of the force exerted by the brakes to bring the car to rest? We have FG here. We have FM here. So we have the constant force applied by the brake that's taking it from this velocity, this speed, 65 kilometers per hour, to 0. So in this case, we have this initial this V naught, which is the initial speed, and the final would be 0. Okay. So in this case, we will use the motion equations. Uh, Let me just get the formula here from the sheet. Okay. So as you can see in this problem, we have the gravitational force. Trying to project the gravitational force on the surface. This one will be FDX, and this one will be, if I'm assuming that this is X, this is Y, then this one, we call this one X, and this one is Fy, where Fy equals to Fn, and then I have the gravitational force being projected as Fx, and I have the uh, the force applied on the brakes as Fv. So in this case, I know the initial velocity, which is 65 kilometers per hour. Final is 0. So 65 multiplied by 1000 divided by 3600. I have P0 as 18.1 meter per second. And then the distance, let me see, I don't know, I don't have the distance. I have the time. So in this case, I don't have. Okay, I can calculate the acceleration. So in this case, I have Vx equals to Vx naught plus Ax t. So I have this one to be 0, and I have dx as 18.1 meter per second. I have the time. I can calculate the acceleration. So here, 0 equals to 18.1 plus 3.7 ax. Then ax would be minus 18.1 divided by 3.7 ax as minus 4.88 meter per second squared. So we have a deceleration here. So we have the car decelerating due to that brake force that is applied till it reaches the stop. Okay. So we need the force. So once we have the deceleration here, we know that delta F equals to ma, right? So now we have the acceleration, which is negative. We have the mass. We have the net force, which is basically FB, if we're taking the positive direction and this direction, then we have Fx minus Fb equals to ma. So we said F, Fx is Fg cosine 18, which is mg cosine 18 degrees minus Fb equals to ma. M is 1.2 to the power 3 times the acceleration here, which is negative 4.88. Substitute n 1.2 to the power 3 times 9.8 times cosine 18.95 minus FB equals to 1.23 times 4.88 equals to minus 5.86 or 3, then FB as 11.7 to the power 3 plus 5.86 to the power 3. 18 degrees from the horizontal. Yeah, yeah, it is sine. It is sine, not cosine. It is sine because this is 18. This is my angle of projection. It is sine. So let me see here. So instead of 0.95, it will be sine 18.3. 0.31. So this number is now 0.23 times 9.8 times 0.31. It is 3.65 to the power 3. And this is plus 5.863 is 9.5. Yeah. How much time does it take for the head to slow down? The speed of the wave. So we have a speed at, let's say, initial equals to 6.6 meter per second. v, say v x now, v x becomes 0 in a distance of 2 millimeters. So this is the distance that he is uh, hitting on. So we have, let's say, 2 millimeter with a Vx 6.6 meter per second, and here Vx 0. Determine the magnitude of the acceleration. So 2 millimeter. Now we have the distance. Now we have the initial and the final speed, and we have the distance. So in this case, we can use Vx squared minus V x naught squared, that equals to 2ax x minus x naught. So this x minus x naught is 2 millimeter. Unit is a meter. We need to calculate the acceleration, knowing that this is 0 minus 6.6 squared. So in this case, we have ax equals to 6.6 squared, and it's 43.56 minus divided by 10.34 minus 3 acceleration as divided by 4 minus 10.89 meter per second squared. So this is the acceleration. How much time? Then you can go to the equation that has the time here, which is we have v x as vx naught equals to ax t. You have the acceleration, you have the initial and the final speed, then time as minus 6.6 divided by minus 10, 9 to the power 3, and then time as 6.1 to the power minus 4. Okay, is that clear? Any questions so far? What is the ratio of the magnitude of the force exerted by the tree on the head to the magnitude of the force of the gravity on the head? So here the head is again hitting horizontally. No information are given about the the mass of the head or the mass of the bird. So you have this head that's applying force right on the tree. As I said, assuming horizontal motion. Hitting right on here, digging in for 2 millimeters. Now the gravitational force for the head is right here, perpendicular, but there were no information given about the bird physical. Okay, so in this case we will have to, I'm sure something is going to cancel when it comes to the mass. So in this case, if I'm talking here about this ratio being Fc over Fg, then Fc as Fc equals to mass times this acceleration that we found, right? Fg is also mass, however, times the gravity. In this case, the mass is going to cancel, and you are only going to end up with the ratio between the acceleration that you found. So R is AX, which is we found here to be 1089 to the power 3. And again, here, let's take the magnitude because we only worry about the ratio. So this one is going to be 8.89 to the power 3 divided by 9.8. So this ratio is, if you assume that this is 10, it will be almost 10.89 to the power 2, approximating this to be almost